A very warm good morning to my all present here. I'd firstly like to invite our coordinator and co-coordinator of FDP to welcome our today's first session chair, Dr. Anand Sharma sir. Ajay sir. Now, introducing Dr. Anand Sharma sir, he is an assistant professor in the Department of Electronics and Communication Engineering at Motilal Nehru National Institute of Technology, Allahabad. With a robust educational background, he holds a PhD in microwave and antennas from IIT Dhanbad and actively engages in research areas like antenna design for IoT, smart antennas using machine learning, and more. Currently, he imparts knowledge in courses like radar and satellite communication, showcasing expertise in analog and digital electronics. As an IEEE and IET member, Dr. Sharma brings a wealth of experience to his role as the session chair for his session on antenna design for 5G and beyond. I would like to welcome sir to begin the session. Thank you, sir.
Thank you so much. First of all, I am thankful to the organizer, Dr. A.K. Singh Saab and Rajesh Kumar sir, for inviting me in this Atal FDP. As in line with this, actually the title of this FDP is some design and implement issue of 5G wireless communication network. So I will discuss the antenna designing part. What are the challenges? What are the requirements for 5G and beyond? If I am talking about the antenna, because as all of you know this thing, that antenna is a backbone of your wireless communication system. First, you have to design an efficient antenna that can support your wireless communication system, that having a very actually in 5G, if I am talking about the 5G and beyond, then we are mainly talking about the data rates, okay, reliability of the communication system. So you have to design an antenna that can support such type of system. So what are the requirements? We will see.
That's it.
Okay. Now I start with a very basic thing. I think all of you know this thing, that what is antenna. Nothing is new in that. I think all of you heard this thing, that antenna is a metallic device for radiating or you can say that for transmitting or receiving the radio waves. Okay. But why I am putting this slide here? Actually, my specialization, my research specialization is basically a dielectric resonator antenna, and I will talk in this in whole this presentation. I will talk about the DRAs, how the DRA works, how it is important for designing the 5G antennas. Okay, because right now DRAs are widely used for designing the antennas for 5G and beyond. Okay, so why I am putting this slide here? If you see carefully, that in 1965, Webster Dictionary, if you see the book of Balani's Antenna Design and Analysis, then he mentioned in that book, in the chapter first of this book, that in 1965 antenna defines as a metallic device for radiating or receiving the radio waves. It is in 1965, which is given by the Webster Dictionary. In 1983, actually IEEE slightly modified this definition, and IEEE says that it is a means for radiating or receiving the radio waves. I think it is clear from these two definitions that basically both the definitions are same, only the metallic word removed from the definition. Okay, in 1983, IEEE removed this metallic word from the definition of antenna. Okay, why it is so? Because a US based scientist named as Professor L.C. Sen experimentally proves this thing that it is not mandatory that metallic device is used for radiating or receiving the radio waves. Now the ceramic materials are also used for radiating or receiving the radio. He experimentally proved this thing, that the ceramic material is also capable of transmitting or receiving the radio waves. Okay, that's why the IEEE modified this definition and removed the word metallic from the definition. Now, what is the idea behind this? So we will go long back. Actually, in 1939. I think all of you are aware with the resonator one. In microwave, there are you have seen the cavity resonator, metallic resonators, where we put a rectangular waveguide and just open both the ends or sorted both the ends. And this type of device are known as metallic resonators. And metallic resonators are basically used for designing the filters or the oscillators, because it actually stores the EM energy. It is not used for transmitting the radio waves. Okay. Now the problem with the metallic resonators is that it stores the storage capacities. You can say that the storage capacity is limited. Okay, limited for the cavity resonators. While if you see, that's why the Richmeyer in 1939 developed the concept of dielectric resonator. He used the ceramic material to store the EM energy. Okay, I think all of you are aware with the dielectric waveguides. The dielectric waveguides. I think in optical fiber we are using the dielectric waveguides. So in dielectric waveguides we have two different types of modes. One is known as a confined mode, another one is non-confined mode. So if the mode is confined, that means all the electric field energy are confined within the structure. Okay, within the ceramic material. This concept is used by the Richmeyer, who is the US based scientist, and developed the concept of dielectric resonator. Okay, where it stores the energy. Oh, what is the advantage of dielectric resonator? Oh, what is the advantage? Advantage is very clear, that if you change the permittivity of the material, if you change the dielectric, the permittivity of your dielectric ceramic material, and if it is increasing, then what happens? I think all of you are aware with the Q factor. Q factor, there is a parameter Q factor. If you increase the permittivity, your Q factor will increase, and as the Q factor is increases, the bandwidth becomes narrow and the selectivity will be very high. Okay, this is not possible with the metallic resonators. In metallic resonators, it is not possible. Okay, so while in ceramic material we increase the permittivity, Q factor is also increases, and the selectivity of your filter is increases. This is the advantage of dielectric resonators. Okay. So in 1939, theoretically Richmeyer developed this concept, while in 1960 this concept is converted into the device fabrications. Okay, the fabrication of the filters, microwave filters, oscillators. Okay. Now, but there is a problem of associated with the dielectric resonators, and the problem is that, as I already told this thing, that there are two modes. There are two modes actually present in the dielectric waveguide. One is known as confined mode, another is non-confined mode. In non-confined mode, the boundary is not perfect. I think all of you are aware of this thing that in metallic resonators, the boundary condition is tangential component of electric field is 0. That's why when the wave strike on the surface of the metal, it will bounce back. Okay. But in case of a dielectric resonator, because this boundary is not perfect boundary, where the tangential component of electric field is not exactly 0, that's why some of the part of electric EM wave is bounce back and some part is go through the surface into the space. Okay, so this is the problem. So that's why which is not actually useful when you design an oscillator or a filter, because there is no there is a requirement of no radiation losses. Okay, while in case of a non-confined mode, there is a radiation losses. Okay, so we when we design the filters or oscillator with the help of dielectric resonator, then the designers use the metallic cavity over the resonator so that the radiation losses are confined within that area. Okay. Now the same drawback of dielectric resonator is used by these three scientists, SA Long, LC Sen, and Mike Baxter, okay, of US. And he experimentally proved that as you reduce the dielectric constant of the ceramic material, then more and more losses are there, more and more radiation losses. Radiation losses are enhanced. Okay, as you decrease the permittivity of the ceramic material, more radiation losses are occurring. Okay, and use this concept, use the same concept, and prove that the dielectric resonator also used as an antenna. Okay, it is also used as an antenna. And after 2000, or you can say that after 2010, it is widely used. This dielectric resonators antennas are widely used in antenna design. Now, ISRO and DRDO widely use this dielectric resonator antenna for satellite communication systems as well as for the radar system, because it having a great capability. Now, as I discussed, this is already I discussed this thing, that when you excite the ceramic material, when you excite any ceramic material, some standing waves are created. I think all of you are aware of the standing waves. So these standing waves, let us suppose that if this end is open and this end is also open, so it will behave like a λ/2 resonator. Okay, and when you excite this ceramic, some waves, some EM waves are excited inside it, and some standing waves are created. When the wave are strike on the surface, some wave is reflected, some wave is transmitted into the space, and as this radiation loss becomes more and more as you reduce the epsilon r of this ceramic. Okay, so now why we go for dielectric resonator? As you are aware with the microstrip antenna, I think all of you are aware with the microstrip or patch antenna. It is compact in size, while we are enhancing the size of the antenna in case of a dielectric resonator. So what are the advantages? So advantage is very clear, that if you are using, as I think in case of a metallic antenna, as the frequency increases, then the skin effect is more dominant. Okay, as the frequency of operation is going towards higher side, that skin effect is more and more dominant. Okay, so now we are in 5G in 5G we are talking about millimeter wave frequency, or in 6G we are talking about the terahertz wireless communication system. So if you are moving towards the millimeter wave or terahertz, then skin effect is highly dominant in that case, and your your antenna gain is going drastically down. Okay, so this is the problem with this patch antennas. If you are designing the patch antennas on a high frequency side, then its gain is very less. This is the problem. While in case of a dielectric resonator antenna, we are using the ceramic material, and if you are using ceramic material, then there is no such type of losses occurs. So we get good gain and higher efficiency if you are designing the antenna on millimeter wave frequency range or a terahertz frequency range. Okay. Another thing is that surface wave losses. I don't know how many of you are aware with this surface wave losses. It is highly dominant phenomena in case of patch antenna, microstrip antenna, because as the wave microstrip antenna is actually radiating through a fringing fields. Okay, and in case of fringing fields, first the wave is going in the air, then into the dielectric, and then after that it is terminated to the magnetic. So when the EM wave is moving from air to dielectric, okay, then there is a if it is moving from air to dielectric through a critical angle, then it behaves like a waveguide. Then substrate behaves like a waveguide for that, and the power at the edges of the substrate, the power going scattered. Okay, so this type of losses are known as surface wave loss, and this phenomenon does not occur in case of a dielectric resonator antenna. Okay, next thing is that why control over the size and bandwidth. Actually, if you see the size of the size of a DRA, then it is directly proportional to lambda and inversely proportional to root epsilon r. So as the wavelength of your operation is increasing, it is decreasing as the frequency of operation is increasing. So wavelength is decreasing and size is directly proportional to lambda. So size is also decreasing. As you are moving towards the high frequency range, your radiator size becomes lesser and less. Okay, it has become more compact. Next thing is that bandwidth. If you can easily control over the bandwidth in case of a DRA, like if the epsilon r is reducing. If the epsilon r of any ceramic material is reducing, then its quality factor is reducing, and its bandwidth, because the bandwidth is inversely proportional to the quality factor. So as the quality factor is reducing, your bandwidth is increasing. So you can easily control the size and bandwidth of a dielectric of a DRA with the help of simply changing the material of your ceramic. Okay. Another important advantage of DRA is it is available in different shapes. Okay, like it is available in cylindrical shape, it is available in rectangular shape, it is available in hemispherical, and each shape having its own advantage. Okay, like if we have a cylindrical shape, then we have three different modes. I think all of you are aware with the T mode, TM mode, transverse electric, transverse magnetic, as well as in case of a dielectric waveguide, we have a third important mode, which is a combination of these two, TE and TM, and that is called as hybrid mode. Okay, HE mode. Okay, so TE and TM, I think all of you are aware with TE and TM, and hybrid is where the EZ and HZ, both the components are present. In case of a TE, EZ component is 0, In case of a TM, HZ component is 0. While in case of a HE mode, both the modes, both the waves, that is electric field in the direction of propagation, magnetic field in the direction of propagation, it is not equals to 0. Exactly, it is not equals to 0. While EZ is dominating or HZ is dominating, this is the different case. So we have 3 different modes. In case of a dielectric resonator, one is T, another one TM, and third one is HE. And each mode having its own radiation characteristic. That means I have given one example to you that let us suppose that if T mode is generated inside your radiator, then the pattern is tilted in some direction. It is not exactly broadside. Let us suppose that this is the radiator and your if T01 delta mode is generated, then it is tilted in this direction. The radiation is tilted in this direction. Okay. If hybrid mode is generated, then the radiation pattern is in this way. Okay. If TM mode is generated, then we have a monopole type of radiation pattern. Okay. Each mode is supporting the different types of radiation characteristics, and it is used for different applications. Let us suppose that if T mode is generated and the radiation pattern is tilted, then it is widely used in satellite communication, for satellite to satellite communication. Okay. Similarly, if TM mode is generated and your radiation pattern is monopole type of radiation pattern, that it is widely used in vehicles, in cars, all type of monopole antennas are mounted on car. Okay. Or several other vehicular applications are there. Similarly, if we have a HEM11 delta, then it behaves like a broad-sided radiation pattern in this direction. Okay, so each mode having its own radiation characteristic. This is the another advantage of DR. Okay, you can easily achieve the different types of radiation pattern by simply switching the modes. Okay. And the last thing is, which is very, very important, it is having high dielectric strength. Okay, you can give a more power to the antenna and it is withstand, its characteristic is not changing with the power. Okay, while it is not a case in microstrip antenna. If microstrip antenna having some limitation about the input power, if the input power is exponentially increasing, then its characteristics is degrading. Okay, that's why this type of antenna is widely used in radar communication. Okay, where we have a very large amount of power we have to transmit. Okay, in satellite communication. Okay, so this type of antenna is widely used in such type of applications. Now, I already discussed all these things, that cylindrical DRA having a different advantage, rectangular DRA having a different advantage. That here, in case of a rectangular DRA, you can easily control the quality factor. Okay, while this is not a case in case of a cylindrical. Cylindrical supports the 3 different types of mode, so we can achieve the diversified radiation pattern through easily through the cylindrical DRA. Now come to the research areas. What we are doing actually not right now. This is the most famous research areas in case of DRA, where you can generate a multi-band antenna. Multi-band, I think all of you are aware with the multi-band. Multi-band means we have a one band and it is the single antenna supports the multiple frequencies at the same time. Okay, let us suppose that we have 2 different bands for W length. One is 2.4, another one is at 5.5 gigahertz. And if your antenna is supporting both the bands, that is 2.4 and 5.5, then it is called as a, you can say that it is called as a dual band antenna. Okay, and in between the spectrum is rejected. Okay, it support 2.4 and 5.5. And in between that the spectrum is rejected by the antenna. So such type of antenna are called as a dual band antenna. Similarly, we have a triple band, a quad band, a pentaband antenna, and that comes under the category of multi-band antenna. Okay, so multi-band generation in DRA, a very famous area for research. Circular polarization generation in DRA is also another area. Okay, I think all of you are aware with the polarization term, orientation of electric field, that is known as the polarization. Okay, so we have a elliptical polarization, and there is a two special case of electrical polarization. One is known as a linear, another one is a circular polarization. Okay, linear having another classification like linear polarization having two different classification. One is vertical polarization, another one is horizontal polarization. Okay, so similarly, circular polarization also having two different classification. One is left-handed, another one is right-handed. Now, I'll come to this part that why circular polarization is important in case of an antenna. So, if you see, my antenna is normally linearly polarized. Okay, and if your antenna is linearly polarized, then it receives the maximum power if the polarization is matched. That means transmitter polarization and the receiver's polarization, receiver antenna polarization. Let us suppose that my transmitter is vertically polarized, vertically linearly polarized, then your receiver antenna is also vertically linearly polarized. Then only it receives the maximum power. Then only it receives the maximum power. Otherwise, you will get a cross polarization. Okay, that is the wastage of power. While if I am talking about the circular polarization, in case of a circular polarization, what is the condition for circular polarization? The condition is that we have a two orthogonal field component that is equal in amplitude. Ex is equals to Ey, and the phase between Ex and Ey is 90 degree. Okay, if this condition is satisfied, let us suppose that Ex and Ey is equal and the phase difference between Ex and Ey is 90 degree, then the antenna can receive power equally in all the direction, equally from all the direction. Let us suppose that my transmitter antenna is vertically polarized and receiver antenna is circularly polarized, then it receives the power very easily. Okay, because we have Ex component and Ey component, both are equal and having a 90 degree phase shift, so there is a circle. Okay, so it receives the power from any direction. Okay, so that's why if I am talking about the satellite communication, when we transmit the data from ground station to satellite, and we have so many atmospheric layers, ionosphere, troposphere, so there is a very high probability that the polarization got changed. Okay, when we transmit the signal from ground station to the satellite, there is a very high probability that your transmitted polarization will change when it reaches to the satellite. That's why in satellite communication we are using the circularly polarized antenna so that it can receive the signal with any polarization, with any type of polarization. Okay, so this is the advantage of circular polarization. Wide research is going on this field, circularly polarized antennas. Either it is a microstrip antenna or a DRA or any other type of antenna. There are so many types of antennas there. Another thing is wideband or ultra-wideband DRA. It is also a very famous area to designing a wideband where we have a very large, you can say that bandwidth. It supports, let us suppose that if I am talking about the UWB, ultra-wideband, so FCC recommends that the ultra-wideband is from 3.1 to 10.7 gigahertz, such a larger bandwidth, up to 7 gigahertz. Okay, so there are different techniques available in literature to design such type of antenna, wideband or ultra-wideband. And fourth and very important one, which is widely used in 5G communication system, is a MIMO antenna. MIMO antennas, where we have a multiple antenna on transmitter side, multiple antennas on the the receiver side. Okay, so it will, I will discuss later on what is that, what is its advantage. Okay, now come to the serial device, that how can we generate the multi-band characteristics in DRA. So multi-band characteristics, there are so many techniques available in literature. I summarize this thing in 3 points. One is by using the multiple DRAs. Multiple DRA means, let us suppose that if I am using the 3 DRAs of different size, then each DRA is radiating in a different frequency.